Okay, can I be heard?
Yes, you.
Great.
And we can see your slides. Yes.
All right, I'm having trouble with Zoom here. I want to say I'm bummed I have this conflict today because I have to walk in on the end of what sounded like a really interesting talk. And yeah, so so yes, I'm sorry. I was trying to switch gears from what it was I was doing before.
Yes.
Yeah. Yeah, my name is Whit, and I'm Whit Schonbein. I'm from Sandia, and this talk is in the general domain of offloading, but it's sort of a black sheep at this conference. Steve Poole reached out to me and said you should submit to the workshop. And he said it could even be about lib fabrics. And I said, okay, I'll take it one step further and I'll make it about portals network API. So it's a black sheep in the sense it's not really it's not really directly related to UCX, but it is related to offloading. But I really hope people find it somewhat interesting, and it's been really I've been very much enjoying the workshop so far. And so I hope to continue to be involved. Okay, so as I mentioned, this is sort of a black sheep talk in that it's about portals, and the topic is basically about leveraging offloaded capabilities that are in the portals network API to enable intelligent NICs. And so, of course, I'll just start by talking about what an intelligent NIC is. You all know what an intelligent NIC is. I'll just say that we tend to view intelligence on NICs as sort of going across a continuum. You can view that continuum in terms of tasks, from simple tasks to more complex or advanced tasks. You can look at it from plasticity of those tasks, that they're fixed, or that maybe they change quite a bit, or they're very fluid. Or you can look at that continuum in terms of the hardware substrate, in terms of in the sense that the hardware needs to support, right? It needs to support the types of tasks. And as you know, naive or non-smart NICs tend to be on the left-hand side of this, and the smart NICs are on the right. And you can obviously see this in the current smart NIC offerings, right? That they tend to emphasize programmability in the form of CPU cores or FPGAs, and sometimes some more task-specific type of processing. But if you were at the SmartNIC birds of a feather, or perhaps the SmartNIC panel at HPC, the consensus seems to be that it's interesting technology, but the jury's sort of still out for how fully programmable NICs might be important for HPC. And so one possible future is that the emphasis on fully programmable for HPC might move a bit back to the left, and it may end up emphasizing more task-specific hardware accelerator components that are on the NIC, in which case intelligence looks perhaps a little less like just being fully programmable, but more like trying to coordinate a bunch of more task-specific offloading hardware. Now, I don't know, I'm just speculating. It's sort of, that trend sort of happened right back in the 90s with active networks sort of giving way to open flow. But well, anyway, we'll see. So a smart NIC, of course, is something that can be configured to perform arbitrary tasks. It's programmable in some sense, but also, as I just mentioned, that intelligence or that programmability could involve coordinating heterogeneous task-specific accelerators. So that's sort of what I'm sort of thinking of when I talk about enabling intelligence. So portals, I mentioned this is going to be about portals, and it's sort of an outlier at this workshop. Portals is emerged from Sandia, and it's a network programming API. It's very hardware oriented in the sense that the capabilities that are identified in the spec are intended to basically be mapped more or less straightforwardly to hardware, so to offloading hardware. That means the capabilities it identifies are relatively simple, right? And so the question we've been sort of asking is how can portals be leveraged, the capabilities it does have, to support more intelligent offloads? Okay, so what I'll say is a little bit about the current capabilities that are in the API, and even if you're not familiar with portals, the concepts are super simple, or it's going to be super familiar. On the left here, we have a portals table. It has a number of entries. Attached to an entry can be some matching elements, right? They have match bits. So this is sounding very familiar, and they specify buffers. There's a DMA engine and an ALU. And so a put, of course, will be very MPI-esque. Come on in, go through the portals entry, match against matching element 2 or ME2, and then the DMA will write the payload to the buffer. An atomic, similar path, except now, of course, it's going to perform an atomic operation and then write the results out. And then when these sorts of events occur, there's an event queue, right, that generates information that the host can use. And then Portals also supplies a lightweight event in the form of counters that can be attached to buffers, and the counters are updated. So I'm assuming all of this is relatively familiar. They're updated when the buffer is written to. And that can be updated by the number of bytes or just incremented by 1 to indicate that a write has occurred. And then this is where the whole triggered operations thing comes in, which one hears about quite a bit these days. When a counter is incremented, if there's any triggered operations associated with that, the thresholds X, Y, and Z here are checked against the current value of counter. If the counter is greater than or equal to the threshold, they get triggered. And they get issued. So this is just an example of a put on an atomic coming in, and X satisfies this condition and gets triggered, Y satisfies it, and Z doesn't. And then they're removed from the list. Okay, so that's the basic components, pretty straightforward. Well, the question we were asking was, all right, these aren't intelligent on that programmability side of the spectrum, right? They're maybe in the middle. They're pretty straightforward. They're pretty fixed in what they do. Can they be made intelligent? So, basically in asking this question, we sort of identified 4 ways to extend the Portals API that would enable intelligence on one of these NICs. In a way that's different than just slapping a CPU on there. So I'll just run through those really quickly. So currently in 4.2, there's some amount of target side resource management that's available. Obviously, the matching elements can specify buffers, but they can also specify offsets into those buffers. And when local memory management is enabled in this way, it overrides the offsets that might be specified in an incoming put, for example. And so the first proposal then is to extend this target side resource management to include allowing the target to specify atomic operations or a subset or a superset of atomic operations. And these would be specified in the matching element. So that's the first proposal. The second one concerns the triggered operations. I mentioned in the previous slide that after a triggered operation is triggered, it's removed from the list. This could be unfortunate, right? If what the triggered operations are doing is a communication pattern, for example, that's going to be invoked over and over and over again, it might be nice if the operations were persistent, right? So they wouldn't have to be reinstantiated. And that could be particularly problematic or annoying, right? If they're being triggered from an accelerator, you don't really want to interrupt what the accelerator is doing or stop or make it wait while these triggered operations are reinstantiated. So for this sort of reason, we want to propose a mode where the triggered operations are persistent, they don't get removed, they can be disabled or they can be removed explicitly, but otherwise they stick around. And then the third proposed extension to the current portals, it concerns the triggering conditions, right? I just mentioned that the current conditions are an operation is triggered when the counter is greater than or equal to a threshold. This is pretty coarse-grained control of what operations get triggered. So we propose a version, an option or a mode that allows for strict indexing, which requires the counter to equal the threshold. And that just gives you more fine-grained control over the triggered operations. And then finally, the final update in terms of proposed extension concerns the way the counters can be updated. Right now, as I mentioned, they can be updated by the number of bytes that are written, or they can be updated +1 to indicate a write has occurred. So what we were proposing in this regard was a special form of ME specified operation that performs a conditional counter update. And that's, it's actually very straightforward, right? The basic idea is the counter gets updated to one of two values depending on the outcome of an evaluation of a condition, right? So if the contents of the buffer specified by the matching entry is less than or equal to 0, then set the counter to one value. Otherwise, increment it as normal, for example. Okay, so those are the four proposals that are sort of on the table, extensions that are on the table. And what they do is they allow, a much finer grained control of triggered operations. So this is just a super simple, very simple toy example. We have one rank, and I'll just run through it really quickly. It puts to rank 1, it puts rank 0 puts to rank 1 the value x. Let's say it matches against the matching element 1. That element specifies a multiplication operator using an ME specified operation, which obviously multiplies the contents of the buffer by the incoming value x and places that in the buffer. That increments the counter, which then triggers this triggered put, which has a threshold of 1. It basically just sends a put back to itself. It doesn't matter what the payload is. It'll be empty. That then matches ME2, which then executes this conditional counter update. Right, if the buffer is less than or equal to 0, then set the counter to 10, otherwise set it to 2. And so then one of these two triggered puts then is issued depending on the outcome of that test. And so rank 0 is now going to receive either a 0 or a 11. Okay. That's a super simple toy example. It's not anything we probably want to do, but it illustrates at least 3 of the 4 extensions that I just mentioned. It has ME specified operations. It uses the new conditional counter update that I mentioned, and it relies on the strict indexing insofar as triggering this 10, this one with the 10 threshold, does not also trigger the one with the 2. It doesn't require persistence. But it wouldn't be hurt. It wouldn't not work if persistence were enabled. Okay, so that's the basic extensions and how they allow a more fine-grained control of triggered operations. So how does this come back to intelligence? So right here, I just have basically a reorganization, a redrawing of the basic pathway that I was talking about before, about having a message, it matches, this operation is performed, and there's a trigger. And basically, you can view this as a primitive, right? Basically, as an instruction, right? That can a potentially binary instruction that has one operand specified by the matching element, a second one specified by the incoming message. The ALU executes the operation specified by the matching element, and then the counter here is a program counter, and it's basically responsible for being incremented and then which triggering the next instruction. And so then a program is just a sequence of these instructions showing the same counter. And then it's not too difficult to formalize this and prove that it's Turing equivalent. It's quite straightforward. So the upshot of this, at least theoretically, is that with these minor extensions, relatively minor extensions, to the current portals API, you can basically enable Turing equivalence, the ability to basically compute or perform any of the tasks that a CPU would perform, which isn't going to say it's going to perform it as well, but yes, in principle, it's as intelligent. Okay, so what we did then is, if you've ever tried coding with triggered operations, you will know it's a huge pain in the neck. And so one of the things we did is we tried to abstract this a bit further. And stick it into the context of an ecosystem, which we call INCA, or in-network compute assistance. And so the basic idea here is well, we can encapsulate this concept of this primitive of an instruction in terms of something that looks like this. It looks a lot like an assembly language, and it basically has all the different components of this of the instruction up here. And once you put all those together, sort of into a language, we have something we call INCA A for INCA assembly. Okay, and then below this in the ecosystem, we've implemented a way to basically translate INCA A, codes written in INCA A down into Portal's API calls. And this involves basically a layer here, an abstraction layer that simplifies the Portal's API and makes it look a bit more like calls that would correspond to Inca A sort of instructions. And then this is just a stand-in for a Python script that we have that literally just translates the Inca A down into Inca lib. And then on the top side, we have a higher level language we call Inca Q and a compiler that'll generate Inca A code. So you can actually code something like this, which is a dot product, 16-element dot product, feed it into the compiler, and out comes Inca A code to perform that. And then these can all be translated down into Portals calls and Portals API calls and executed, for example, on an extended version of the Portals reference implementation. We also have an interpreter that we've constructed, and a module for this interpreter is a simulation module that'll give estimates on runtimes. And I'll go ahead and show, these aren't all that important, but I'll go ahead and show them to you. So using Inca Q, we can code up a variety of just kernels. We thought somebody might say they wanted to do at some point in offloading. And then these are just some of the configuration we used for these particular numbers: 400 million messages a second in nanosecond on NIC scratchpad memory, and 8 kilobyte payloads, and then so you can see the runtimes here in microseconds. And to put it in a little bit of context, we don't expect this to be fast, right? And that's in comparison to CPUs, and it's not. In comparison, it's an order of magnitude or two slower than, say, a 3.2 gigahertz Haswell for this matrix multiplication. And again, that's not really that's not surprising. This isn't really intended to be an alternative, competitor to CPUs. The real idea here, I think, is more like that second notion of intelligent, to basically be able to enable some sort of intelligent or programmable way to coordinate the use of on-NIC accelerators. So let me give a super simple example of that, about the simplest example we could come up with. So here's that pathway again. So a very simplest, accelerator we could think of would be something like a SIMD unit, something that did SIMD instructions, right? And so if we assume there's also this SIMD unit available to do these vectorized instructions, but this can be integrated into Inca A by simply adding more instructions into Inca A. In this case, it's multiplication on multiple elements, hence the M. In this case, it does 256. Otherwise, the parameters here are the same, and that obviously is the threshold. I just cut and pasted this out of one of our Inca A codes that use this, and then we went ahead and we extended the simulator and extended the interpreter to deal with these. And so just for completeness, here's a comparison of the runtimes from out of the simulator. These are some of the kernels that were amenable to parallelization using these instructions. We also did some stuff to avoid data movement. That's what the C's stand for. And these were the values from the previous. And here's some the new values. So we're getting some reasonable speed ups. But again, I don't think the point here is necessarily to try to compete with CPUs. Really, what we're trying to think of here is what this example is supposed to illustrate is how could you integrate new accelerators into this sort of system as facilitated by this extended portals, right, and the Inca ecosystem over it. And so from this perspective, really, what this sort of instruction represents is sort of a method for steering the data to the appropriate accelerator that's available. And then it's embedded in this larger context of the program that coordinates or steers that data through the available hardware accelerators. And so this is just, so that's sort of the broad vision behind what we're looking at here. So I just wanted to summarize really briefly. I haven't been keeping track of time, so I hope I'm not too fast or too long. What I've done here is basically just explain how we have some relatively simple, straightforward extensions to the current portals that enables intelligence in the sense of being programmable. And that's sort of facilitated by this Inca ecosystem, makes it easier to see that. But it also hopefully enables this intelligent or programmable coordination of heterogeneous task-specific accelerators in the context of the portal's processing pathway. Okay, and I also just wanted to mention, this is material that will be a topic of discussion. I'm going to make it a topic of discussion in the Portals group in the future, perhaps for some of it to be included in Portals 5, but discussion has not started yet, has not begun yet. Right now we're focusing on Portals 4.3, which should be out in February or March, and it's much more incremental update to Portals. But if anyone's actually interested in this anymore, I'm the new Portals point of contact with Ryan Grant's departure to Queen's University. And here's my email address. If you have any questions or interested in dropping in on a Portals meeting, just let me know. The portal specification used to be located here. It's been broken, so I apologize. There's a version on ResearchGate. I'll try to get this fixed. And then finally, the portal's reference implementation is located here. We have a version, a branch that has these extensions implemented. It's not public yet, but I'll be trying to get that out there as soon as possible. So thank you, everybody. And I hope there was something interesting in there. And so I'll stop.
Thank you very much, Whit. Are there any questions from the audience?
I just have one comment. With Portals community always welcome to UCX forum. Probably Oscar remembers, but actually on the first workshop, which was I think 5-4, 8 of us in the room. Ron Brightwell and Barney were presenting Portals. Oh,
really? Okay. I mean, I know there's a long history here.
I think it was 2014, so I don't know. It was a long time ago.
Oh, wow. Okay.
Oscar, do you remember?
Yes, I do. We are all good friends. So.
All right. Okay, good. Yeah, because Portals is what Portals is. And despite I've spent a lot of work in Portals and now I'm forced to work in Portals, it is what it is. I enjoy it, but I know some people, sometimes I hear snarky comments occasionally. I'm sort of, hey, I just the messenger. So yeah, so.
No, it's all good. Sandy actually one of the biggest deployments of UCX as well. Astra
right.
system.
Yeah, I was going to say
Astra system.
Yes, yeah. My experience with UCX has been having to re-roll it because the default installation on Astra doesn't have multi-threaded support enabled, and so I was trying to use MPI thread multiple. So and then also we messed around with the UCX support for hardware offloading on ConnectX-5 is something else. So no, I just haven't done anything within UCX, but
yeah, I'm not surprised yet to install. I remember we were patching up release as it was installed on Astra.
Yeah,
cool. Thank you. Very interesting talk. Very interesting approach of SmartNICs.
Yeah,
very quite different one.
Yes,
it does reminds a bit of P4 and eBPF work, but a bit different.
Yes.
Yeah, it's strange. I recognize it's different. I don't really have a lot to say to that comment. But it did occur to me because I was watching the talk on active messaging the other day, and it occurred to me that this is sort of like a low-level active messaging interface on something like this, right? Because you can define as arbitrarily complex handlers on the receiver side, but at the level of triggered operations.
Yes, one of our active message benchmark I think we implemented is was inspired by some other people. Indirect put, essentially, we have the triggering operation essentially was hash function that was placing in memory based on some hash indexes and so on.
Right. Yeah. This is related to some work, that I'm forgetting his name. Some people have done a key value store, implemented over portals. And then obviously this is, I don't know if you're familiar with Ryan's RVMA paper or work on RVMA.
Yes,
RVMA is basically portals with the receiver side memory management, right? And then setting up portals tables and matching elements as sort of the virtualization of the address space. So this is related to that, and in a sort of sense can be viewed as sort of an extension of those same principles to basically trying to coordinate potential accelerators, because again, I don't know what your views are on the future of SmartNICs. Obviously, in HPC, I just don't know what the future is going to look like there. And so, and again, the need might be there for coordinating a bunch of different heterogeneous types of accelerators. I imagine GPUs, and if you really want a CPU, you can always put a CPU on here, right?
And this is one of the times when more recent SmartNICs, DPU, IPU, whatever people call it, where you have application class cores sitting on the NIC. The fun part that it's really driven not by HPC community, it's driven by hyperscalers, so it's completely different use case.
Right, absolutely.
And HPC community is trying to piggyback on this and see if we can do anything useful with it, right? It is programmable, but in some sense it's very different because we have fully bloated Linux running on it. So it is. I envision that we'll see very, very interesting and different approaches. People trying to figure out how to use it.
Right. So I don't know if you were at. We ran a birds of a feather session on SmartNICs at SC. And Hari was there talking about, tag matching offloads on blue fields and offloading collectives. And then Rich Vuduk was there talking about offloading some aspects of mini-MD onto blue fields. And the open question that sort of emerged was, well, maybe for collectives, acceleration in the switch or offloading in the switch might be more effective than offloading on a blue field. And then, and for tag matching, I mean, obviously one of the points of portals was supposed to be use TCAM for tag matching. So keep it really fast. So again, that goes back to you have specialized hardware basically for doing you have ASICs for doing tag matching rather than something fully programmable. And then Rich's point, he got some really interesting results, but the amount of work required to refactor the mini-MD code to offload the right components, it was a lot of work figuring out what to offload. Was a lot of work. So you can't really. It's hard to see. DPUs, for example, as just being like a GPUs are right now in HPC. There's something that scientific programmers would offload too. So it's a really open. Obviously, we don't need a lot of the packet processing or virtualization or some of that stuff, in depending on the HPC system. So so it's just sort of an open question right now, I think. But we're hoping to advance it forward, a little bit with this discussion.
Yes. So yes, it's a very interesting approach, especially with the I think it's called the Inca A architecture, and it will. I'm just wondering if you are targeting potential compilers generating, just like compilers can generate a SIMD or vectorization code. Is it part of the idea that you will use some sort of compiler technology to generate some of these instructions, or is it more, or it's going to be more like a user API that you envision that will enable these sort of things?
Yeah, it's part of the vision part of the vision, of course, is that someone who actually knows how to do programming languages and compilers will actually take over that, that part. My hope is that you could do something like, just integrate Inca, what we were calling Inca Q, just make it some sort of subset of C. Use something normal and then use pragmas or something to mark it as something that's to be compiled to put on a portals NIC. And just like you use pragma and pragmas to say these are going to be SIMD and then different portals NICs could have a core instruction set that's just based on the standard ALU and the whatever you want to say is the standard in portals, and then you could have extensions and they could provide compiler components that would compile to their extended to whatever hardware support they offer. That's the vision anyway, but right now I'm the only one doing this, and there's tons of work in optimization.
Yes,
there's so much stuff you could do to make it run more efficiently.
Yes, yeah.
So
anyway, yeah, it's very, yeah. I really appreciate your talk. Was very, very interesting. So it's very interesting because we cover so many different levels of abstractions here to program smart NICs. Starting from cloud native, basically very high level abstractions, to all the way to iFunc, OpenMP offload, and this approach that is a instruction level approach. And yeah, it seems to me that there is a lot of efforts, and we should be learning from each other on the different approaches and abstractions.
Cool.
And
well, thank you.
Yeah, and thank you very much for your talk.